Today we will discuss about Euler's theorem for homogeneous function. So before starting of Euler's theorem, we will understand about the homogeneous function. So definition of homogeneous function: a function fxy is said to be homogeneous function of degree n if it can be written as f of xy is equal to a0 x raised to the power n plus n a1 x raised to the power n minus 1 into y plus a2 x raised to the power n minus 2 into y square plus a3 x raised to the power n minus 3 into y raised to the power 3 plus and so on plus an y raised to the power n. So every term of homogeneous function have the same degree. Okay, so every term of the homogeneous function. So this we can write down as we take x raised to the power n as common. So this can be written as a0 plus a1. So this will be y upon x plus a2. Second term will be y upon x to the whole square. a3. Third term will be y upon x raised to the power 3 plus and so on. This term an y upon x raised to the power n. Okay. So this expression we can denote it as function of y upon x. So this equal to x raised to the power n function of y upon x. So this is called homogeneous function. So we can write is called homogeneous function of degree n. Okay. So when we find the degree of any homogeneous function, so we should make that particular function in this form. So for example, the function of xy given as x square plus 2xy plus y square. So we calculate the degree of this homogeneous function. So when we calculate the degree of this homogeneous function, we take x square as common. So we write down this as 1 plus 2 into function of y upon x plus y upon x to the whole square. So y upon x to the whole square. So that means this we can write as x square into, this is the function of y upon x. So here the n represent the degree of the homogeneous function. So here the power of x is 2. So that means this is the second degree homogeneous function. So here the n will be 2. So this is the second degree homogeneous function. So this function having the degree 2. So degree is 2. Okay. So homogeneous function, every term of the homogeneous function have the same degree. So you can directly check the given expression. So that means having degree 1, 1, so 2. We have two variable x and y. So we add the degree of both the variables. Okay. So power, so that means x having power 2, x and y having power 1, 1 in second term, and y also having the power 2. Okay. So hope you understand the homogeneous function. Now we move to the main topic, that is the Euler's theorem. Okay, so the Euler's theorem. So we have statements of Euler's theorem. So let z is equal to fxy be a homogeneous function, be a homogeneous function. So then x del z upon del x plus y del z upon del y is equal to nz. Okay, so this is the statement of Euler's theorem for two variables. So two variable means x and y work as independent variable, or another form we can write down as x del f upon del x plus y del f upon del y is equal to n. Okay, so we shall prove this. So proof of the Euler's theorem. So let yeah, directly we write down. We know that the homogeneous function, general form, uh, homogeneous function of degree n is z is equal to x raised to the power n function of y upon x. So this is equation 1. So z equal to fxy or fxy equal to x raised to the power n. We take the statement directly from the homogeneous function definition because this is equal to f of xy. Okay. So z equal to fxy. So we take as z is equal to x raised to power n into function of y upon x. Now we see the LHS. Okay. So we see the LHS of the Euler's theorem is x del z upon del x plus y del z upon del y. So first we differentiate equation 1. So we write down as differentiate 1 partially with respect to, when we differentiate partially with respect to x, so we write down as del z upon del x is equal to first function xn, and differentiation of second, this can be written y dash y upon x into differentiation of y upon x is equal to minus y upon x square plus differentiation of first and x raised to the power n minus 1, and we write down the second function as it is. So we multiply both sides. Multiply both sides by x. So we see that. So this can be written as x del z upon del x is equal to x raised to the power n minus 1. So because we have 1 upon x square, and into y phi dash y upon x plus n x raised to the power, and when we multiply with by x, so this gives us x raised to the power n pi y upon x. So this is our equation number 2. Now differentiate again equation 1 partially with respect to y. So we see that del z upon del y is equal to, so x raised to the power 1 treated as constant. So the differentiation of function phi is phi dash into y upon x, or by differentiation of y upon x is 1 upon x. So now We multiply both sides by y. So we see that y del z upon del y is equal to x raised to the power n. So y upon x into phi dash y upon x. So this can be written as x raised to the power n minus 1 into y phi dash y upon x. So this is our equation number 3. So we add the equation 2 and equation 3. So we see that the LHS of Euler's theorem is x del z upon del x plus y del z upon del y is equal to minus x raised to the power n minus 1 into y phi dash y upon x plus n x raised to the power n function y upon x plus x raised to the power n minus 1 into y phi dash y upon x. So this term will cancelled by this term. So we see that the RHS is n x raised to the power n function of y upon x. So here we use the equation 1 for this one. So we write down as using 1. So this will equal to z. So we see that. So x del z upon del x plus y del z upon del y is equal to nz. So this is our Euler's theorem for two variables, x and y. So we can extend the Euler's theorem for three variables. So for three variable, we take as if u is the function of three variable x, y, z. So then the Euler's theorem can be written as x del u upon del x plus y del u upon del y plus z del u upon del z is equal to and u. So this can be extended for three variable as well as for n variable. So n variable means if u is equal to function of n variable x1, x2, x3, xn. So then we write down as x1 del u upon del x1 plus x2 del u upon del x2 plus x3 del u upon del x3 plus xn del u upon del xn equal to n u. So this theorem can be extended for n variable. Okay, so thank you.